Okay, so now when you talk about friction, of course, you need to first know it particularly before we look at the inclined plane or what. You need to first know what friction is. Okay, friction basically is the force that opposes relative motion between two bodies in contact. Okay, so we've got friction of two types, where we have static friction and the dynamic friction. Okay, but when we say static friction, that is the frictional force that exists between two bodies in contact that have got relative motion with respect to each other. No, not relative motion. When we say static friction, that is the frictional force that exists between two bodies in contact which have no relative motion. Static, they are stationary, they are not moving. But when we say dynamic, that is the frictional force that exists between two bodies in contact that have relative motion. Okay, so for dynamic, they have got relative motion. It is the frictional, the force that opposes relative motion between two bodies in contact that have relative motion with respect to each other. Now, before you attempt any number this side, you need to be knowing the laws of friction. Laws of friction. Frictional force acts in opposite direction to the motion of the body. If the body is moving upwards, and they say the frictional force acted upon the frictional force acted upon the body, it means that now the frictional force will be opposing motion. So if the body is moving upwards, the frictional force will be acting downwards. All right, that is the first friction. Number two, friction opposes the movement of the body across the surface. All right. Then still, you need to know that if bodies are in equilibrium, the frictional force is just sufficient to move and increases as the tendency to move increases up a limiting value. We shall keep looking at these things. We shall keep looking at these things as we progress. Then another thing you should know is to know that the magnitude of limiting friction for given surfaces bears a constant ratio to the normal reaction, meaning that the frictional force over the normal reaction bears a constant ratio, which we call mu. So that's why we come up with an idea that F equals to mu r.
Mu r.
Okay, because frictional force bears a constant ratio with the normal reaction of the body. Which constant ratio is it? Mu, and that is what we call the coefficient of friction. And this mu depends on the nature of the surfaces in contact. It depends on the nature of surfaces. All right, F is the limiting friction, R is the normal reaction, mu is the coefficient of friction. All right, now I'm going to give you a general assumption. If we suppose a horizontal force may be P, if horizontal force P is applied on a body on a rough horizontal table, I'm beginning, though my main emphasis is planes, but I'm giving a general idea using a table. If this horizontal force P is applied to a body on a rough horizontal table, the body does not necessarily move. There is a frictional force, for example, let me call it F. there is a frictional force F that opposes the applied force P. And this frictional force, okay, this frictional force for a particular surface is not constant. It increases, the frictional force increases as the applied force P increases until this F reaches a maximum force, which you call F max, beyond which it cannot increase. When the body is just about to move, it is said to be in a state of limiting equilibrium. And at this point, the maximum frictional force is equals to mu r. We shall use this equation very oftenly, very oftenly. So when the body is just about to move, frictional force is equals to mu r. But when the body starts to move, the frictional force takes its limiting value mu r and acts in the direction opposite to that relative motion, or to that of the relative motion of the body. There are some important notes I want you to make, or there are some important notes I want you to know. You need to know that the frictional force, exists between the body and the surface in contact. Frictional force does not act on the body. For example, these sketches normally bring students down. If you have a certain body on the table, if this is my body, and this is the normal reaction of the body, and this is the force pushing the body, force P, the weight of the body would be mg. Now, if the force is pulling the body this side, then the frictional force will be acting this side. So here we have our F. But I want you to know that this frictional force must be acting between the body and the surface in contact. It shouldn't be on the body. The moment you label it, or the moment you move the force F on the body, you get it wrong. Are you getting my point?
Yes.
The same applies on the inclined plane. If you're having an inclined plane, if it is an inclined plane, it must be inclined on a certain angle, maybe alpha. If this is the body, it will have weight mg. If the body is m kilograms, it will have weight mg, and it will have normal reaction r. And if it is being moved upwards by force P, then the frictional force will be acting downwards, F. But this F shouldn't be on the body. It should be between the body and the surface in contact. That is on the plane. Are we together, Seb?
Yes.
Anyway, this one will take us to what we call the, let's go direct to the inclined planes, and we see how we can exploit inclined planes. Inclined planes. Now, when you look at an inclined plane, and I want to first begin with what we call the angle of friction, because the angle of friction is the one that will take us to prove some of the things. So we need the angle of friction. Now, it should be noted that if maximum frictional force and the normal reaction are compounded into a single force called the resultant of friction, or called the resultant reaction, then the angle formed between the normal and the resultant is what we call the angle of friction. What am I trying to mean? If we have the normal reaction R and the frictional force, maximum frictional force F, all right? If these ones are compounded into a single force called the resultant, so if we have the resultant here, okay, let me call it S, the resultant, let me call it S, okay? Then the angle formed between the normal reaction and the resultant, the angle formed between the normal reaction R and the resultant S is what we call the angle of friction. And that one is denoted by lambda. So if you complete this, It means that still here we have F. All right. Since this one is F, even this one will be F. Now, from this diagram, we can deduce that tan lambda is equals to tan lambda will be opposite, which is F, over adjacent, which is R. All right?
Yes.
But F over R, we say that this is the ratio of frictional force and normal reaction is a constant, which is mu. Do you remember? F over R is mu.
Yes.
So tan lambda is equals to mu. But what is tan? Tan is the same as sine lambda out of cos what? Cos lambda. And this is equal to
Lambda.
mu. Implying that lambda is the same as tan inverse of mu from here, isn't it?
Yes.
But still you need to know that wherever we shall be, when we are proving wherever that is mu, for us we can really put sine lambda over cos lambda. All right? So today's lesson is going to explain to us how we resolve forces along the plane and something like that. So today's lesson is we are going to be looking at derivations. Then maybe we shall look at questions where we are applying. But you need to know that this is very important. Okay. Now.
Yes.
Let's say particle on an inclined plane acted on by an external force. And we have cases we consider. Cases considered. Case 1. Force acting parallel to the plane required to move particle upwards. Force acting parallel to the what?
To the plane.
Parallel to the plane required to move the particle up. But still, when these cases are being considered, here I'm going to begin with a case where the angle of friction where the angle of inclination of the plane alpha is less than angle of friction, angle of friction lambda. Then we consider this case. When the angle of inclination alpha is less than the angle of inclination lambda, it means that the plane is gentle enough to enable frictional force to prevent the particle from sliding down. Since the body is moving up, and we have said that the angle of inclination is less than, it means the angle of inclination, since the angle of inclination is less than, the slope is going to be gentle. Are you getting? Not like this, otherwise we would have drawn like this, and we be like this. almost like this, to be like a triangle. But here the body is gentle, rather than the slope. The slope is gentle. So we want to look at a case where the force is acting to move the body up. So if this is the angle of inclination, alpha, all right? And maybe I have the body of mass, m kilograms. If the body is of mass, m kilograms, then the weight will be mg, isn't it?
Yes.
If the weight is mg, this body has got what we call the normal reaction acting. So we have what we call the normal reaction R. Then here you can include these other forces. We have mg cos alpha. However, these forces one can leave showing them, one may not show them because these are the components of the inclination of the body. Then here we have also got mg sine alpha. Are you getting that?
Yes.
But they are saying that force acting parallel to the plane required to move the body up. Maybe let my force be P. Are we getting?
Yes.
If the force P is to move the body up, then it means that the frictional force will be acting downwards since the body is rough. Are you getting all what I've written?
Yes.
Now, from this sketch, you can resolve forces very, very, very easily. We shall begin by resolving forces along the plane. When we say along the plane, that is parallel to the plane, the forces facing up should counterbalance the forces facing down, meaning that P, since P is the only one facing up, are you getting? P would be equaling to F plus mg sine theta, sine alpha. You add this. You get the ones in the same direction, you equate them to the ones in different direction. As simple as that. So P is equals to F plus mg sine what?
Sine alpha.
Is that hard?
No.
But P is equals to F. You know that F is mu what? Mu R plus mg sine alpha. If I call this one 1, then now I resolve perpendicular to the plane. Resolving perpendicular to the plane. Perpendicular to the plane. Now I'm looking at the vertical forces. I have R, and R is counterbalancing mg cos alpha, right? You don't talk about mg because mg, you resolve the mg with respect to mg cos and mg sine. So you don't talk about it. So you talk about R facing up equaling to mg facing down. Is that clear?
Yes.
Is that clear?
Yes.
So now we can substitute the value of R into this equation 1 because we have R. So because we need to get the magnitude of P, right?
Yes.
So substitute R is equals to mg cos alpha into equation 1. So you'll have P is equals to mu. Then instead of R, we shall write mg cos what? Cos alpha plus mg sine alpha. Is it clear, Sebo?
We have substituted R into the equation 1.
Yes, I've just put R into this equation. Okay?
Yes.
So this is going to be P is equals to mg is common, isn't it?
Yes.
So into mu cos alpha plus sine alpha, isn't it?
Yes.
This mu, we had already seen what mu is equals to. We said that mu is sine alpha over cos alpha. So it is sine alpha over cos alpha times cos what? Cos alpha, then plus sine alpha. Okitegedde?
Yes.
So this is going to be mg into LCM is cos alpha. So here we shall have sine alpha cos alpha plus.
Couldn't
Oh no.
cancel.
No.
Couldn't cos cancel.
This would be sine mu. You remember? The
Yes.
angle of friction. Mu is the same as sine. Actually, sine lambda, sorry. Let us get this step from here, from this step, from P. Let's take it to this side. So we've gotten P is equals to
mg into,
it was mu mg cos all right. So this
yes,
is it. Mg mu cos alpha plus sine alpha. So this is mg. Instead of mu, we shall write sine lambda over cos lambda, then cos what? Cos alpha
cos alpha plus
plus sine alpha. So this is going to be mg into sine lambda cos alpha plus sine alpha cos lambda over cos alpha, isn't it? Over cos lambda, sorry.
Cos lambda, yes.
Now, what does this one equal to? Here you have to bring in the trigonometry. So this is going to be mg. You need to really understand that sine alpha cos sine lambda cos alpha plus sine alpha cos lambda. This is an expansion of sine of
Alpha
lambda plus alpha. Isn't it?
Yes.
Everything out
Yes.
of cos what? Cos lambda.
Cos lambda.
This is the same as mg sine lambda plus alpha sec lambda as our P. Is it okay?
Yes.
Where the sec came from 1 over cos. The whole
Yes.
of this, then times 1 over cos. You get that. So that is how we come up with this. Is it clear?
Yes.
Then now let's look at a case where we have force acting parallel to the plane required to move the body down. Me, provided you learn how to resolve, every other thing is going to be very, very, very fine. Force, case 2 is force, where we have a force acting parallel to the plane required to do what? To move required to move the particle down. Are you seeing that?
Yes.
So this is still my alpha. This is my body of weight mg. This is R. Mg cos alpha. And this is mg sine alpha. But now they are saying that The force is required to move the body where? Down.
Downwards.
So force P is acting like this, isn't it?
Yes.
Now where will the frictional force be pointing?
To point up.
But on the plane, not on the body. So this is where we have F.
Yes.
So can we fail to resolve forces?
You can resolve.
Resolving forces along the plane. Along the plane, you will be having along. You'll be having F. F is the only one pointing up, isn't it?
Yes.
And the one is pointing down are P
Equaling
and
to-
mg. So we shall have P
Yes.
plus mg sine alpha equaling to what?
To
To
F.
Which together, implying that
Yes.
P, because we're interested in force P, is equals to mu r minus mg sine alpha, isn't it?
Yes.
Because F is mu r, so we subtract this. I call this one equation star. Then I resolve perpendicular to the plane. When resolve perpendicular to the plane, what are you having? You'll be having r
R equaling to mg
cos
theta.
alpha.
cos alpha. So
Then you substitute r into equation star. Substitute r into star. So it will be P is equals to mu mg cos alpha minus mg sine alpha. Are you getting that?
yes.
So this is going to be mg into mu cos alpha minus sine what? Sine alpha. Are you getting that?
Yes.
So this is going to be equal to mg, but mu is the same as sine lambda over cos lambda times cos alpha minus sine alpha. So this is going to be mg into, when we take the LCM, to be sine lambda cos alpha minus sine alpha cos lambda over cos lambda, right? So this is going to be
yes.
mg, the expansion of this is sine, but this time lambda minus alpha, isn't it? Out of cos alpha. All right?
Yes.
Which will be mg sine lambda minus alpha sec lambda.
Then sec.
Provided you know where is the force taking the body, and you know that the frictional force will be acting opposite to the direction of the body. Could there be any problem?
No.
These ones you have to learn them properly. Can I rub and I put another condition?
Yes.
What about a case where we have a force acting at an angle theta a force acting at an angle theta to the plane required to move the body up. a force acting at an angle theta to the plane. At an angle theta to the plane. What does it mean? It means that here a force is also inclined.
Yes.
So now, the moment we are looking at this, we have to first sketch. Without a sketch, there is nothing. So if the angle of inclination is alpha, then here is the body of weight m what? mg.
Mg.
You have the horizontal component mg cos alpha
And mg sin alpha.
mg sin alpha, provided you see a point of moving the body up, it means that the frictional force is down. All right. Then, of course, the
Yes.
normal, we've got the normal what? The normal reaction. You must use a ruler when you're drawing this. Everything you must use a ruler. But they are saying that the force is acting at angle alpha, angle theta, meaning that now the force is no longer straight, but it is acting at a certain angle theta. So my force P is acting on a certain angle what? Angle theta. Meaning that if P is acting on a certain angle theta, it has to also be resolved. Are we together? Anything that acts on an
Yes.
angle, you have got to resolve it. Meaning that here, you'll have P cos theta, the horizontal, and here you'll have P sin what? P sin theta, the vertical force. Are you getting my point?
P cos theta is facing upwards.
Yes. Because the body is moving up. So since the body is moving up, you cannot move the component of P. All these components are attributing to P. So you cannot move them down. These are components of the force P. A component of a certain force, it's like a catalyst. So when you make them face down, that is something that is very, very, very unfortunate. It has to face up.
Yes.
So now, resolving along the plane. Resolving along the plane. Which forces will you be having along the plane? We have P cos theta equaling to isn't it?
The P sin theta is considered with the arrows.
P
Those
sin
ones
theta
that are
is
facing up.
P sin theta is up. We are looking at along the plane. Along, we are not looking at perpendicular to the plane. Along the plane, you consider the forces which are on the plane. Are we together?
Yes.
So you're having P cos theta is equals to F plus mg sin alpha. Is that okay?
It is okay.
Implying that P cos theta is equals to mu r plus mg sin alpha.
Alpha.
Then perpendicular to the plane. Perpendicular to the plane.
Perpendicular to the plane, R plus P sine theta equaling to mg plus mg cos
I beg your pardon,
alpha.
R plus
R plus P sine R plus P sine, that is theta, then equaling to mg
you
plus
never
mg cos alpha.
consider mg. Mg has got its components, mg cos alpha, mg sin alpha. That's why we have not considered the p. We have considered its components, p cos and p sin. So never should you consider anywhere this mg. I think from the previous example, we have not considered anything like mg anywhere. We consider its components.
Yes.
So it is r plus p sin theta is equal to
mg cos alpha.
Is equal to mg cos alpha. Here you can get r. Your r will be so you can substitute 2 into 1, right?
Yes.
What shall we be having? P cos theta is equals to mu r. R is mg cos alpha
minus P sin theta.
So
plus there is something else.
Plus mg sin alpha, right?
Sin alpha. Yes.
So we can say P cos theta plus mu P sin theta, isn't it?
Yes.
Is equals to mu mg cos alpha plus mg sin alpha, isn't it?
We have brought
I've brought mu p sin theta this side so that I correct them together, the p's.
Yes.
So here we shall have p into
cos theta plus mu sin theta.
Plus mu sin theta is equals to mg into mu cos theta plus sin alpha. It is cos alpha plus sin alpha, isn't it?
It is cos alpha.
So wherever mu is, I'm going to substitute. So it will be p into cos theta. Mu is the same as sin lambda over cos lambda. So I will say cos theta cos lambda. I've substituted it already. I'm assuming that you have understood what mu is equal to.
Yes.
Then plus sin theta sin lambda, everything is over cos lambda is equals to mg into, since mu is sin lambda over cos lambda, so it will be cos alpha, cos alpha sin lambda plus sin alpha cos lambda. Everything is over cos lambda. I think you know how these ones have come about. I've substituted for mu as what? Sin lambda over cos lambda. So now this is an cos plus sin. This is an expansion of cos to be p cos theta minus lambda. This is an expansion of cos minus. All right.
Yes.
But these cos alpha, cos lambda and cos lambda, they will cancel. So I will have mg this side, cos sine, sine cos. That is,
What about the cos lambda down?
it has cancelled with this. So I'm having mg sine. Have you understood it?
Yes.
Alpha plus lambda. Is that okay?
Yes.
Implying that my P is going to be mg sine alpha plus lambda out of cos theta minus lambda. Sometimes they ask you for the minimum force. For minimum force, you need to know that for minimum, if they need minimum force, okay? For minimum,
Yes.
the denominator cos theta, that is from your trigonometry. Cos theta, I think I taught you this. Cos theta minus lambda should be equaling to 1, meaning that theta minus lambda is cos inverse of 1, meaning that theta minus lambda is equals to 0, cos inverse of 1 is 0, meaning that theta is equals to lambda. So if they need a minimum force, P minimum would be equaling to mg sine alpha plus lambda. Because if theta is equals to lambda, then this one would be 0, because 0 is 1. You get the point?
Yes.
So is resolving still a big problem? It is a matter of knowing
No.
how to assemble your thing. Now, let's live another, then I give you live examples with values, okay? Force
Yes.
acting at angle theta to the horizontal, a moment. Hello.
Yes.
We are saying that we are considering a case where we are having a force acting at an angle theta to the plane. Sometimes they say horizontal force. We shall look at the cases of examples. The plane required to move the particle down. Required to move the particle where?
Down.
Now let's sketch. During the sketching, you must use a what?
A
A
ruler.
ruler. This is mg. Mg equals alpha. Mg sine alpha, but this is R. They have said that the body is to move where? Down. So my frictional force should be
Downwards.
moving where? Up. Am I right?
Upwards. Yes.
Then they have said force acting at an angle theta, meaning if the body is to move downwards, now the force will be acting this side, downwards, right? So if this is my P,
Yes.
now I have to put its components. You get the point?
Yes.
Now, meaning that my horizontal component would be moving down because it is a supplement to mg sine alpha. You get the point? So this here I have my P cos theta here. If it is a theta, are you getting my point?
Yes.
I have P cos theta. Then still this one here, this P will keep a supplement to R, P sine theta. Implying that now I can resolve very well, isn't it?
Yes.
Resolving along the plane. Along the plane we are having, tell me now, along the plane.
Along the plane, we shall say F equaling to P cos theta plus mg sine alpha.
Mg sine alpha, that's good. But we need P. So we can say, Carl, even if you leave it there.
We can say P cos.
Then, Carl, first give me the perpendicular to the plane.
Perpendicular will be P sine alpha.
P sine alpha.
Sorry, P sine theta.
P sine theta.
P sine theta plus R equaling to mg cos alpha.
Very good. Now, if I leave it here, can you drive it up to the final answer?
I can derive it.
So I want you to drive it and see if you get the minimum P as mg sine now. It will be lambda minus alpha. Okay.
Yes.
Now, can we do some examples?
Yes.
Because here, I will not do you too much. I will not do you too much. I want to assure you that I will not do you too much. Again, you need to know that I'm not going to do you too much, but instead, I just wanted you to be very, very much aware about resolution of these forces, okay?
Yes.
But examples, we shall pick most of them from the QB. Okay, we shall pick most of them from the QB. You're right, a body of mass 8 kilograms.
A body of mass 8 kilograms.
A body of mass 8 what?
Kilograms.
Is resting on a rough plane.
Is resting
on a rough plane. Of inclination 30 degrees to the horizontal.
Inclination 30 degrees
to the horizontal. Comma. The coefficient of friction being mu. The coefficient of friction being mu. Full stop. Continuation. The least force acting parallel to the plane. Acting parallel to the plane. That will move the body up is 60 newtons.
That will move the body up
is 60 newtons.
Is 60 newtons.
Full stop. Find the value of mu.
Find the value of mu.
Now, such a question should not give you any hard time, because you really know what to do. First sketch. We have those problems which involve motion, but for now, let's. So the angle of inclination have been given as
30.
they have said that the least force acting prior to the plane that will move the body up is 60 newtons. So that force is here. 60 what?
Newtons.
But the body is of how many kilograms?
8 kilograms.
So if the body is 8 kilograms, what is its weight? 8g.
8g.
Implying that if the weight is 8g, it has got the components. Which components include 8g cos what?
Cos 30.
And this is 8g.
Sin
And it's the
30.
normal reaction. But by mere telling you that the body was rough and the force is moving it upward, it means that the frictional force is moving it downward. Can that sketch, if you are marking, can you deny a mark on this sketch?
No.
You give a mark. If a student is missing this or has drawn it badly and is having right answers, can you mark them?
If the sketch is wrong.
And is having right resolved forces, can you mark them? If you are the one marking? No, because that student is going to make a wrong engineer who will just put the building on when he has forgotten some brick somewhere and the building collapses. This is mechanics. What you draw means what you put. Okay? Now, resolving forces along the plane. Resolving forces along
the plane.
Tell me. Shall have 60.
You can say 60
is equal
to F plus 8g sin 30.
So 60 is equals to mu what? Mu r plus 8g sin 30. Call it equation 1. You resolve perpendicular now to the plane. Perpendicular to the plane. If you resolve perpendicular to the plane, you'll have r. Let's save time. R is equals to 8g cos 30.
Yes.
Then you substitute r into equation what? 1.
Equation 1.
So you'll have 60 is equals to mu r. So it will be mu 8g
into 8g cos 30.
Cos 30 plus 8g sin 30, right?
Yes.
So 60 is equals to mu times 8 times g. You use what they normally give you on the cover page. Cos 30 plus 8 times 9.8 sin 30. So 60 is equals to, when you compute this, 8 times 9.8 times cos 30, it's going to give you 67.8964 mu, plus when you compute this, 8 times 9.8 sin 30, you get 39.2. Okay?
Yes.
Implying that when you subtract this one from this side, you'll get 20.8 is equals to 67.8964 mu. When you divide both sides, you get your mu as 0.31. What is hard? Is there anything hard here?
No.
Now, before we go to those ones of motion, I want to give you some questions that I need you to really calculate for me. A particle. Now, these ones which I'm giving, you are the ones to do, you are the one to do them. A particle,
yes,
of mass 0.5 kilogram is released from rest. Is released from rest and slides down a rough plane inclined at 30 degrees to the horizontal.
Inclined at 30 degrees
to the horizontal.
Full
stop. It takes 6 seconds.
It takes 6 seconds
to go 3 meters.
Go 3 meters.
Full stop. Roman 1. Find a coefficient of friction. Between the particle and the plane. Between the particle and the plane. Correct 2 decimal places. It was specific. Correct 2 decimal places. Roman 2. What minimum horizontal force? What minimum horizontal force? There, that horizontal force has to be inclined. Minimum horizontal force. You get the point? You have to incline it at a certain angle.
Yes.
These ones which we last proved. What minimum horizontal force is needed to prevent the particle from moving? Is needed to prevent the particle from moving. Part A, you should get, or you check if you get 0.557. Part B, check if you get 0.0855 newtons. Okay. Then there's this question which I do believe that it's a proof, but I want you to do it so that in our next meeting, maybe I start from that. I start correcting you from that. Okay.
Yes.
Oh, I've not gotten full of it, but you write this also. A body of mass 8 kilograms.
A body
of 8 kilograms rests on a rough plane. Rests on a rough plane. Inclined at theta to the horizontal. Inclined at theta to the horizontal. Full stop. If the coefficient of friction is mu,
the coefficient of friction is mu.
The coefficient of friction is mu. Find the least horizontal force
Find the least horizontal force
in terms of mu, comma,
in terms
of mu,
of
comma,
mu,
in terms of mu, comma, theta, and g,
and g,
which will hold the body in equilibrium. Which will hold the body in equilibrium.
equilibrium.
We should get this answer. 8g into sine theta minus mu cos theta out of cos theta plus mu sine theta. Are we there?
Yes.